Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm your host, Shafu, and today's guest is Zero H. Zero H, thanks for taking time, man.
Thanks for having me. It's a pleasure to be here.
Yeah, for sure. So Zero H is gonna walk us through Seaport. So yeah, why don't you briefly introduce yourself, introduce Seaport, and then directly jump into the code?
Absolutely. So I'm Zero Age. I am the author of Seaport, and along with the talented team at OpenSea and beyond, we've built a marketplace for buying and selling NFTs and doing so in a really flexible and secure manner. And Seaport is currently in version 1.5. It's had a number of releases to get to this point, but 1.5 is relatively stable, deployed to all manner of chains and L2s. I think we're up to 20 plus EVM chains, and it's powering a lot of really interesting activity.
Nice. That's really cool. Uh, So yeah, I think maybe a good start would be to take a brief look at the diagram you have in the
Ah,
README down below.
sure. Yes. So Seaport is a single contract. There is also a notion of conduits and the conduit controller, which are separate contracts you can approve um, to transfer tokens on your behalf, and then that allows for updating the version of Seaport that you're on. But Seaport at its core is a single contract. However, that contract has a lot of functionality crammed into it. It's quite extensive in terms of what it can do, but the core idea is moving tokens from one place to another. And if you have some familiar with Seaport, you've probably seen this notion of the offer and the consideration. Every Seaport order specifies some number of items, uh, ERC20 tokens, 721, 1155, that are being offered by the offerer, the creator of the order, and then some number of consideration items. Same idea, but they also specify a recipient that should receive those items. Now, to make this happen, the core components are you need to be able to verify orders, which means ensuring they have the correct time, ensuring that they have a valid signature, that their status is correct, that they haven't been canceled on chain. And then once you have valid orders, then there are a number of steps in the process for things like resolving criteria items. Criteria items are when you want to select some token from a larger set of tokens, and you can supply a Merkle root in place of a token identifier. There's also amount derivation. Seaport has baked in a ascending or descending price or amount for any given item, and based on when the order gets fulfilled, that determines the amount that needs to be offered or received back as consideration. And also, you can specify restricted orders, which will call out to a zone as part of the fulfillment of that order. And you can update on chain state, perform whatever checks you need to. All of those checks feed into the execution engine, which will actually perform the token transfers. At the end of execution, every single consideration token needs to be fully provided and met. or supplied by the fulfiller, and then whoever the fulfiller is, the caller can take whatever tokens are remaining. So that's the core overview of all of the pieces. Everything is, if you're looking to familiarize yourself with Seaport, we have somewhat recently changed the layout of the repo. So for a long time, Seaport was just one big mono repo, but there are a lot of contracts, especially tests. So in order to make it easier to build extensions to Seaport or Seaport apps, which we can get into a little later, we've created a number of modules that you import. So Seaport types is the first of these modules. It just contains all of the interfaces and some helpers, and the main thing are the structs and enums that are used throughout Seaport. This is the standard order struct, order components, and you can see it contains the offer of the order, the zone, the offer and consideration arrays, which are arrays of items, an order type, start time, end time, zone hash, which is information passed along to the zone when you make a restricted order check, a salt, which just provides some entropy, a conduit key, which determines what conduit the offerer wants to use, and a counter, which is a per offerer value that can be incremented at any time, canceling any open orders that were signed with that counter. So Seaport types is then used by two distinct repos. One is Seaport core. Seaport core inherits the types and contains all of the optimized smart contracts. So, or they all cascade down into Seaport here, but there are a number of these libraries that are all imported in a somewhat complex dependency graph. And so this is where you would want to turn if you are building some extension to Seaport. Then you would pull in Seaport core and you have all of Seaport available and ready to use. It's not necessarily the right place to start if you want to write tests for Seaport or familiarize yourself with that, with the way it works. In that case, you would want to come just to the Seaport repo, which inherits from Seaport core and contains all of these reference contracts. The reference contracts are one-to-one equivalents to the optimized versions of each of these, but there's no assembly code. And they've been specifically designed to be readable and digestible, and aside from the gas usage and to the best of the constraints of the Solidity language, when you don't drop down into assembly, they're exactly equivalent. The other repo that I want to point out that also uses Seaport types here is called Seaport Soul. And Seaport Soul is started as a framework for writing better Foundry tests. Basically a set of helper libraries for making logic around how to interact with Seaport more accessible and ergonomic. And this is a very interesting resource. We've used Seaport Soul to create and extend a number of contracts for facilitating safer interaction with Seaport. So one example is the Seaport Navigator, and another is the Seaport Validator. I'll start with the Validator contract. this is back in Seaport, which inherits from Seaport Sol as well. And the validator is a contract that you can call and provide an order, and it will scan the order, check all of the items for the necessary approvals and balances, ensure that the signature is correct, and spit out a list of errors or warnings related to that order. So if you are a power user or you're running a marketplace or an aggregator, then you could use this validator contract to determine whether or not a given order that is submitted or that you're about to fulfill is safe to proceed. And then on the fulfillment side, there is the Seaport Navigator contract. This contract operates in a similar vein. It actually uses the validator as one of the steps, but you provide a group of orders, and it will not only scan each one for validity, but it will also generate all of the criteria resolvers that are required, given a list of the candidate identifiers in any criteria item. It will generate the fulfillments. It will show you exactly what token transfers are expected to occur on simulation as executions. And it will advise on the recommended fulfillment method to call, and even provide the call data for performing that call. So these are all, it's a sort of constellation of helpers on-chain as well as in libraries that are very useful if you are building something that involves Seaport or want to contribute to the core Seaport library. So we may as well jump in on some interesting bits and bobs on the contract. Curious if there's anything that you think would be an interesting place to start.
That's a really hard question, dude. I don't know. What would you recommend? There's so much here.
There is a lot here. I think one good place to get your feet wet on any of this stuff is looking at the token transfer utilities, just to get a sense of what the lay of the land looks like. And as we mentioned earlier, Seaport is really, if you distill it down, it's just about moving NFTs, moving tokens, and under specific conditions. But there's, to do that in an opinionated and optimized way, requires at least using Solidity, which is our lingua franca. It requires some degree of manual understanding of what's going on. Let's take a look here. So if you want to just transfer an ERC20 token, one pattern that we use a lot throughout Seaport is rather than always scattering magic values and relatively arbitrary opcodes throughout assembly, we try to keep it as readable as possible by using named constants. So there's a whole file of constants and others. I mean, there's a lot of constants that are used throughout, but we name those and then use that throughout. And
Yeah, Zero H, could you maybe zoom in a little bit more?
sure. That better?
Perfect.
Great. So in this case, we populate the call that's got to happen to transfer a token and fire off the call. Now, ERC20, there are a number of ways that popular tokens deviate from the standard, and what the standard dictates is that you would return a Boolean true value on a successful token transfer and return a Boolean false value if the transfer didn't work. In practice, what the vast majority of tokens do, which they frankly should do, is they revert if a token transfer doesn't work. But we handle that case where it returns false. There are also tokens that don't return any data. There are tokens that return too much data. All of those are handled with branchless logic. This is another pattern that you see quite frequently is rather than using conditionals, Seaport opts in whatever places it makes sense to take a branchless approach, which means that you're evaluating the entirety of an expression every time and don't have to incur the overhead of jump statements to evaluate things in isolation. In this case, there's the case where you have no data or success. Really, this function is a microcosm of where a lot of the complexity lurks under the hood. This is a fun one. So, assuming that the call failed and reverted, this is another pattern that we use throughout that I don't think is very common, but is interesting. So, when you have a reverted call, there's just like if it was a successful call, it's going to return data. And when that data is returned by the contract that you called, in order to then pass along that revert reason, the data has to be read into memory and then bubbled up via another revert. However, that memory expansion could be prohibitive from a gas perspective. You might not have enough gas, especially if there's a malicious contract that you've called. And remember that anyone can supply any NFT as part of a Seaport order. So if it attempts a transfer and it returns a lot of revert data, then you have the potential for a form of denial of service where you can obscure the actual revert reason by forcing an out of gas error. So it's not in no way is it a critical type of edge case. You're going to revert, but you lose a lot of information about what was causing the revert unless you look and see how much gas is available. And so this is a fun little section where we actually compute based on the size of the return data, the revert reason, the size of memory, we get the cost of that, and then we'll calculate the memory expansion cost based on that size and the current memory size. And if that exceeds the gas cost, then we throw with a generic error. If there's no data returned. So we can still pick out that, okay, this was a token transfer error, and yet if the token transfer returned its own error that provided some additional context, then we would just return that. Oh, okay, I know what we should probably talk about, because this is also a fun component to Seaport. So throughout Seaport, every single entry point, every external function that you can call takes with the exception of increment counter and arguably fulfill basic order, which can be used if an order is pretty pared down. Almost every function uses custom decoders for call data because the structs are quite complex. And the Solidity high-level language, by default, performs pretty rigorous and at times quite redundant checks to make sure that the call data that's supplied to a function is compliant and doesn't have dirty upper bits and doesn't have segments that are out of range or unexpected or that type of thing. That all of the pointers and offsets they're not malformed. A lot of that is it adds something like 10 to 15% overhead over doing what we do, which is manual decoding, especially for the offer and consideration structs. By taking an approach where we punch in and we make a couple of simplifying assumptions. The biggest one is that we only examine the last 4 bytes. I believe maybe 3, but I think 4 bytes of any pointer or offset and mask it so that we can safely we can discount that there may be overflows that are triggered by malicious pointers or offsets that way. So that is it's a deviation from the standard encoder, but one that I think makes plenty of sense. And then just manually verifying each word and only the components of each word in the struct that need to be validated saves a lot. Let me show you the way it works. So you've got like a bunch of these decode functions, which will all roll up into these functions that take call data pointers and memory pointers, and then we cast them. So if we look at, for instance, if we look at one of the entry points, a good example is calling fulfill order here. You'll notice this custom name order. As soon as you name an argument, that is a signal to the Solidity compiler, hey, I intend to use this argument. So Solidity will decode the argument, and in decoding it, it performs a number of often inefficient or redundant sanity checks on the inputs. So by not naming this function, we skip much of that. There's still a little bit that is performed, especially on the top level of was sufficient call data supplied, that kind of thing. But we omit the name, and then we just specify what's the call data offset of this, which in this case it's going to be OX40, right? It's because you have 2 arguments. So we specify the pointer at which this order lives in call data, and then we decode it, and this is a function cast that operates on the call data pointer, and then this is also a cast that will get us back to an advanced order, and then we can proceed as normal. But there's a number of these functions, this pattern where here's a more rigorous one.
Yeah.
This is this is going to look at the call data pointer for this advanced order. This is going to look at the call data pointer for criteria resolvers. It's going to decode each one manually and then convert them to the required types using these wrappers. So now we have, this is an advanced order, this is a criteria resolver, this is a conduit key, etc. So I would encourage anyone to check out, there's a library called Ability, ABI-LITY, by Dylan Keller, who's one of the co-authors of Seaport. And it's been totally worked out to be a generic and more productionized version of this, whereas in Seaport 1.5, it's not directly using Ability, it's using the outputs that were generated from Ability and then worked into the code in a more manual fashion. But I would totally encourage anyone that's curious to check that out. It's got to be one of the top areas where you can squeeze serious efficiency out of most contracts, especially ones that take complex arguments. Let's see. So one thing that we also could talk about here that I think is, given the type of discussion we're having, is the testing framework. As anyone that is working on building smart contracts understands, the vast majority of the work is really in testing and ensuring that it works as expected. And Seaport has had a number of different testing sprints. We started out with a whole suite of hard hat tests, which gave us initial confidence in things like getting to 100% code coverage and ensuring that we had at least direct tests for everything that we needed. We then started dipping into Foundry tests for more of a depth-first test framework, and utilizing fuzzing. However, our initial Foundry test suite was still primarily focused on going deep on single specific features. And we had a number of minor bugs that we discovered after deploying Seaport 1.2, followed by 1.3, followed by 1.4, all related to complex interplay between different features, and realized we needed a more comprehensive way to test different combinatorial feature sets. So this is something I would really encourage projects that have complex interactions or interplay between different features to consider, is some kind of framework like this. So all of these tests, which we refer to internally as the moat tests, they all live in the Seaport repo proper. That's where pretty much all of the tests are found. And if you take a look in tests Foundry new, these tests are actually just a single test. We have this test generate orders. And the way this works is, rather than saying, oh, we're going to test this function, we're going to try these features, like maybe it's got criteria items, maybe it's got a 1271 offerer, so you're using a contract signature, or we say, no, what we're going to do is we're going to generate some random number of orders, random number of items on each order, offer and consideration items, and we're also going to provide a random seed for this specific fuzz run. Then we take these parameters in the seed and generate a brand new order that tries arbitrary combinations. So you would have there's a chance that it's a 1271 offerer. There's a chance that it's a direct signature. There's a chance that it's validated on chain. There's a chance that it's an ad hoc signer, which means that you're fulfilling your own order. And there might be a 1 in 4 chance of any of those being the case. And that it'll perform that for every order in the set. And then it will also take every item and say, oh, there's a chance this is an ascending amount item. There's a chance this is a criteria-based item. Long story short, it's going to just explore a massive design space of all different combinations of whether or not you're using conduits or transferring lots of tokens, few tokens, and then it's going to look at what it generated and take that, and using the same framework as we use with this Seaport Navigator contract I talked about earlier, it's going to figure out a way that it can fulfill that order and execute the test. Well, another component to this is it's not just going to execute the test, it's also going to execute a mutation to the test. So in this case, let's see, does it live here? It's been a minute since I was in this section of the code base. For context on the timing, we released Seaport 1.5. I want to say, it was about 4 months ago, 3 months ago here. And since then, after really building confidence with these test suites, we've turned our focus to enabling people to go out and build Seaport apps and extensions and investing in these tools like the Navigator and the Validator contract and all of that. But
Yeah. Zero H,
this
could you maybe go into more detail regarding the fuzz engine itself?
yes, indeed. So this is, let's see, this is a direct test for, they're all in helpers, I believe, or yeah. Okay. So this is a very useful description of everything, all the steps that are going down as part of this fuzz test framework, which we also then, we have a CI runner that will pull this in, and then you can trigger actions and it'll tap into our cluster and run tens of millions of fuzz runs, which has been an absolute savior during development and just for building confidence that something's going to work even with the long tail of different features that you explore. So first, we already talked about the generate step, and that's the output of the generate step is going to be a space. So rather than picking specific items and amounts and all of that and actually creating the orders, you first create a space of enums that just represents the choice that you're going to make for each of the features that are selected. And then once you have that, it will operate on the space to generate the actual set of orders that conform to that space. Next, there are a number of amendments to the state of Seaport. So we might want to be testing that specific orders that are canceled cause it to fail, or are skipped if you're using fulfill available, which is a fulfillment method that will make an optimistic attempt to fulfill orders, but if they've already been fulfilled, then it skips them without reverting the whole batch. So that's amendment is updating the fulfillment state, the fulfillment fraction for orders. You can partially fulfill orders if their order type allows it. Then once you've amended the state, then we run a whole sequence of derivers which give us the expected executions, is basically the final output there. We get the fulfillment arrays, the criteria resolvers, and the executions. Once we have the executions, then we can run setup and figure out what tokens need to be minted. That's the minimal set of tokens that need to be minted and approvals that need to be set on Seaport or conduits for this to work. And also can prime all of the checks to ensure that balances change appropriately and approvals change appropriately and all of that. And throughout this whole process, checks are being registered as they become relevant. Every time that there's a new order that's added, that's a check that we need to make to ensure that the order status gets set to, okay, the order's been fulfilled, or that kind of thing. Then we execute, and in order to execute, the entire context gets passed off to another contract, which then performs the final call. And in the exec failure case, this is also interesting. Once we've built up this whole big complex payload of what orders are going to be fulfilled, we'll change one specific thing. There are a lot of the fulfillments. Here you can see all the steps, but this exec failure is what we're about to talk about. But then we also run exec success these are in two distinct contexts, and perform the checks in the success case. So we know that the success case all works, and then changing one very targeted thing about it will break everything and cause it to fail. And the failure, let's see. I think that most of the failures are all here. So we select a random failure based on whether or not that failure is eligible for selection. So once you've got all of these orders, if there's a order that contains a fractional component, then you could have a bad fraction where the numerator is greater than the denominator or something to that effect. But if it's all simple orders, you're not using fulfill advanced order, then you're not eligible to select this particular failure. So it goes through and just decides on whether or not it can choose a given failure, and then performs the mutation for that failure once it's been selected. And one other thing I'll mention here, if you're poking around, and I do feel like it's been really been a useful exercise and informative journey to go through this process, because if you look at the Seaport contracts, especially the optimized contracts, it's all in the name of efficiency, right? And that's driven many of the decisions around how we've tried to make it as readable as possible, but ultimately it's all about being efficient. In the tests, it's all about grappling with complexity. And it's a much more complex thing to fully understand the modes of interaction and the interplay between these different features for a protocol than it is to just have the protocol proper. So all of the way that the contracts have been written, there's not nearly as much consideration for efficiency. That's not really the aim. The aim is to make it as ergonomic as possible while being able to handle the complexity. But for instance, like a lot of these there's so many libraries that often are operating in a pretty abstracted way to build up the final set of abstractions. Hence, having a single contract that you call, or single function that you call, that is testing everything. So this framework, this pattern of generating and exploring a really wide space, and not just fuzzing on particular arguments, but fuzzing on the feature set that you're going to explore with the fuzz test, is, I think, a really useful pattern and something that I'd like to see more of.
Mm. And this is in your CI pipeline. So every time you want to merge a pull request or something, this runs.
Correct. Every time that you want to merge a pull request, this it's a relatively small fuzz campaign will be run in the CI in the repo. I think it runs 5,000 or 10,000 runs, along with all of our other test suites and linters and you name it. But then we also have a standalone internal repo that will pull this in, and we can trigger an action to run an arbitrarily large campaign. You wouldn't want to run a 10 million fuzz campaign every time you're checking in a commit, but once we're feeling like, okay, this is, we're getting ready to go to audit or go to production or whatever, then it's very useful. And you do see, like, some of the edge cases that we were seeing, especially in the reference contracts. That's one of the places that luckily we didn't discover any problems with Seaport proper in doing this, but we did discover some discrepancies with the reference contracts, which mostly minor things, but some of those discrepancies would only show up once every million runs or 500,000 runs. Edge cases that required 4 different features to all be present and in a strange order, but you have to explore that. And it's also, those are the types of tests that the only way you're going to find those is through really deep manual review of the code and understanding it really well, or from an exhaustive search of the design space. And even that, there's no way that you're just going to go through, and you might be able to identify that there's a problem and write a reproducible, call it almost like an exploit script. But when you're involving a lot of different functions and features, those are not tests that are going to make it into a code base as a direct test. It's too onerous. You have to find those in a more generic way. So
Yeah, the
anyway,
state
that's
space is just too big, right?
exactly.
Yeah. Wow. This is, I definitely need to take a look after this again.
Let's let's see if we have a. I'll maybe we can find a few more just little fun nuggets in the code base, because I do think that there's there's a lot to chew on in the test suite, and it is absolutely critical to get that right in a project that's as widely relied on as something like Seaport is, but it's also not it's not quite as fun as just picking out like why certain assembly tricks are the way they are. So let's see. What's another good one? The basic order stuff is pretty fun. Basic orders, this is one of the most heavily optimized of the routes. Effectively, basic orders are they're orders where there's only one offer item and one or more consideration items. There's only one NFT across both. There's a whole bunch of constraints on what the order can do. But what we can do in this case is we perform a quick check right at the beginning. I think it's in the encoders, but we basically say, all right, we're going to ensure that the default encoding has been provided, i.e. this parameters input, the pointer's OX20, and we have a single argument. So we make that check, and then once that check has been performed, rather than using the call data pointer throughout and using memory pointers throughout, we can instead just operate on known fixed offsets in call data and in memory. So call data parameters based on whether the order is 721 or 1155 or it's bid side or ask side, we just read whole sections of call data directly into the correct place. So, which is all here. And as we do this, we operate on a couple different components at once. So this is where we ensure that the default encoding is used and do some other basic validation. Get the timestamp, check that that the consideration array hasn't been shortened. But then, what we as we go through the items, in this case, it's just the consideration items that we have to iterate over. We simultaneously are building up so we're looping through them once to build up the order hash, to derive the order hash using the data, and to prepare the event that we're going to emit. And so both are getting populated at once. And finally, once the hash has been prepared, the offer item, there's only going to be one. Same trick though. We prepare the event directly in memory and also prepare the order hash. So once we've done that, we can derive the final order hash, and Yeah, there is a lot to the basic order fulfillment that every line is like a little trick, but all in all, I encourage people to dive in and play around with it and familiarize yourself. I should I should mention that the Seaport working group, the Seaport Discord, is a great resource if you want to ask questions or are thinking about building something on Seaport, or are just curious about some of the design patterns around testing. You can get in touch with all of the various very talented contributors and co-authors and developers that have contributed to building this out. And I'm sure that uh, we're always happy to grow the knowledge on Seaport specific or just best practices that Seaport has helped to popularize. So
Awesome.
I'll share a link with you to the invite to the working group and invite anyone that's interested to come join us.
I will put it in the description for sure. Zero H, maybe one last question. Um, do you think if you have to rewrite Seaport in like 10 years, you would need to use that much of inline assembly? Or do you think that the compiler will be good enough to optimize it to a sufficient level? Or do you think there will always be a space where you just have to go on the assembly level?
You know, I think it's impossible to extrapolate 10 years out in a space that is changing as fast as ours, so I won't opine on that, but I do think that there is a huge potential for better high level abstractions that also let you punch down in more targeted ways where you need to. There are there are a couple of efforts to re-implement Seaport in Viper. We kicked that off early in the life cycle of Seaport, and it actually showed a lot of promise in simplifying a lot of what Seaport is doing. However, and this may have changed, but when we attempted it, there were also some language level limitations that prevented us from really proceeding. What Solidity has right now that other stacks don't is just the benefit of a long history, relatively speaking, a long history of people running into problems and then figuring out workarounds. For instance, a contract as complex as Seaport requires inheritance, right? It all is inherited up into one contract. Viper, at least at the time that we were looking at it, did not support inheritance, which is arguably a feature because inheritance can introduce a lot of weird circular dependency issues or just obscure the intent of code, but it some degree of modularity becomes very important. Viper also deals in static memory allocation, which effectively bounds the complexity of or the size of any dynamic array, which means that you have to be somewhat opinionated about, okay, how many items can be on any given order and how long can any signature be, and so that does limit the flexibility. I think that, and there's also another more nascent initiative to implement Seaport in Huff, which I think would be so cool. But that is the opposite of what you're proposing, which is there a
Yeah.
world where this could be implemented in a more straightforward, more readable fashion? I think it's going to be really fascinating as L2s rise to greater and greater prominence, and the targets for what even needs to be optimized shift away from the, at least on mainnet, the target for optimization is really avoiding storage and avoiding unnecessary memory operations that or redundant memory operations or that kind of thing. Whereas in the L2 context, it's call data is king, and so I could see a version of Seaport that's optimized for those contexts that could actually be much more straightforward. Another thing is the advent of T-Store. Once Cancun lands in the end of the year or whenever that lands, we're anxiously awaiting because there is potential for T-Store to simplify a lot of operations that are currently handled in memory that approximate you can approximate them much more simply using a mapping, right? And we have to perform a full search and scan over array elements where in reality some of those operations can be simplified by just representing things as direct mappings. And so there are, I'm confident that more modular and extensible tools for doing things like embedding Huff and Yule and highly optimized segments into higher level languages and tucking that away or merging those fixes upstream into the compiler. One could imagine something like the ability library eventually making it into the Solidity compiler, and that would obviate the need for a lot of the low-level optimizations. So hopefully we can start picking at that stuff, but there is some degree of structural improvement that you can find by operating on memory and in a opinionated way that is derived from the structure of your specific application. If you're coming at it from a generic approach, then you have to take a more opinion or a more rigorous and potentially redundant approach. I don't know if that makes sense, but
No, absolutely. I think the point you made about the context you're in makes the most sense to me because if you look at the programming space today, right, 99% of people write in some high level language, but if you need to write a driver or a bootloader or something, you don't, okay, maybe you don't write assembly, but at least you have to write C, right? And probably some assembly as well. So yeah, it would probably depend on the context.
yeah. And I should also really underscore that the reason that Seaport was built in the way that it was, highly optimized, lots of low-level code, is so that we could, as a community, as an ecosystem, solve this fundamental problem once and get it right and do it efficiently so that now the complexity and tricky low-level assembly stuff is tucked away in Seaport. And by implementing Seaport apps or contract orders that extend the functionality of your contract to utilize Seaport, or by plugging into Seaport, which is designed from the ground up to make orders and buying and selling NFTs a really composable and frictionless thing where they can fluidly move around. Now the problem has been attacked, and you can just utilize Seaport to perform that pretty foundational requirement of being able to move NFTs under specific conditions. So
Hmm.
the hope is that we don't have to uh, when you're creating your NFTs or your other contracts, they shouldn't need to use all of the low level tricks and bells and whistles because they can just draft off of what already has been thoroughly vetted and audited and tested uh, and utilized in production at scale, and we all can benefit from that shared track record.
It just becomes another layer of abstraction, basically, right? Which
Correct.
awesome. Zero H, thank you so much, man. Thanks for taking the time. If people want to find you, probably the best place is on Twitter, right?
Twitter is a good place, and I I encourage you to come find me in the Seaport Working Group, or
Yeah, for
to
sure.
get involved and open up some PRs on any of these repos that we've worked through today.
Yeah,
Yeah, find me on
if you
GitHub.
wanna rewrite this in Huff, let Zero H know if you're interested.
Absolutely.
So
Yeah.
awesome. Thank you,
And
man.
we're also actively looking for um, new developers to join the team. So we're always interested in bringing on talented devs, not only smart contract, but especially as Seaport matures, we're also really interested in investing in the surrounding infrastructure. So any distributed systems engineers, Rust experts, uh, you name it, I'd love to chat if you
Awesome.
want to
If you have
come work on Seaport and all things NFTs.
nice, if you have a job description site or something, send me the link so I can put that in the description as well.
Great. All right.
Awesome.
Thank
Thank
you so
you.
much. It's been a
Okay,
pleasure.
guys. Yeah, mine. Likewise. Take care, guys. Bye bye.
Bye.